Okay, so hopefully the audio is better on this video. I realized that it was a little not great on the first video that I made, so you might have to turn that up. Okay, so now what I want to do is I want to actually compute the Fourier transform of an actual function. So the function that we're going to be looking at. So this is the definition of the Fourier transform here, just so it's there for reference. And this is the assumption that f is absolutely integrable, meaning this. Okay, so we're going to look at this example. So we're going to say let f of x, this is going to be the function that is equal to 1 for the absolute value of x less than a, and it's going to be equal to 0 for the absolute value of x greater than or equal to a. Here it doesn't really matter whether or not the greater than or equals is there or there. The graph of this function, let's say this is minus a, this is a, it's going to be 1 from minus a to a and 0 everywhere else. And since technically it's 0 and x is equal to plus and minus a, I will write it like this, and then like this. Okay, now the notation that a term that we use for a function like this is we say that it is supported from minus a to a, meaning it's non-zero from minus a to a. Informally, it means it's non-zero from minus a to a. So anytime we have a bounded function, which this is, that is supported on a finite interval, then this is always going to be satisfied. And in fact, we can just compute the integral of this function. It's going to be equal to 2a, which is definitely less than infinity. Well, as long as a is less than infinity. Now, in the case where a is equal to infinity, we have the function that's equal to 1 from x going from minus infinity to positive infinity. It clearly does not satisfy this assumption, but we'll see a little bit later on how we can actually still reasonably define the Fourier transform of that. At any rate, let's look at this function and find the Fourier transform of it. So basically, we're just going to plug this function into the definition here. I'm going to change colors too, just to liven things up a little bit. I think green might not be a great color, but I think purple will be a good color. So f hat of omega, just using this definition here, it's 1 over the square root of 2 pi times the integral from minus infinity to positive infinity f of x e to the minus I omega x dx. I'm just using the formula here. Okay, now what is f of x? Well, if the absolute value of x is bigger than a, it's equal to 0. And then if it's less than a, it's going to be equal to 1. So this then is just the integral. Well, we have this thing here we have to keep writing, but this is going to be the integral from minus a to a on these values of x. F is 1. So this is just equal to e to the minus I omega x dx. And if you want to think about there being 1 like that explicitly, you can. Okay, but this is good. This is an integral that we know how to do. Okay, now keep in mind, x is the variable of integration. Omega is not the variable of integration. So we can just do fundamental theorem of calculus here. So this is going to be 1 over the square root of 2 pi. Okay, we're going to divide by 1 over minus I omega. And then we're going to have e to the minus I omega x, and we're going to evaluate this from x equals minus a to a. Okay, if we do that, we're going to get 1 over the square root of 2 pi times 1 over minus I omega. And inside here, we're going to get e to the minus I omega a minus e to the minus I omega minus a. I'm going to change this right now. These minus signs cancel, and it's just e to the I omega a. Okay, now we can make this look a lot nicer. I'm about to erase these lines and just basically copy and paste this up here. So I'm going to keep this and erase these 3 lines. So go ahead and write that down if you don't have it. or pause the video, I guess. So this, via these computations, this is equal to minus 1 over the square root of 2 pi, 1 over minus I omega, and then we're going to have e to the minus I omega a minus e to the I omega a. Okay. Now here's the thing. This is technically correct. There's nothing wrong with this, but the function that we're given is a real valued function, and so we would like to get out, things that have real values. Okay. So we're going to use Euler's formula. So Euler's formula says the following. Euler's formula says e to the I t is equal to cosine t plus I sine t, and we're assuming that t is a real number. So e to the it is equal to cosine t plus I sine t. If you were wondering why I'm saying this lies on the unit circle, this is exactly why. It's cosine t sine t. If you think about parameterization, it's going to be a parameterization where the parameterization is cosine of t, sine of t, which is something on the unit circle. So this right here is a formula that we can use to write these complex exponentials in terms of cosines and sines. And so that's what we're going to do now. So now what we're going to do, I'm going to have to unfortunately scoot over here a little bit to the left. So we're going to have 1 over the square root of 2 pi. Forgot the minus. 1 over minus I omega. Okay, so here we're going to have cosine of minus I omega a, sorry, not the I, cosine minus omega a plus I sine of minus omega a. And this next part is going to be minus cosine of omega a, and then minus I sine of omega a. Okay, so now we're going to use some properties of cosine and sine. So cosine is an even function, which means cosine of minus omega a is equal to cosine of omega a. And sine of minus omega a, sine is an odd function. So sine of minus omega a is equal to minus sine of omega a. And now we can see what's going to happen. We're going to have 1 over the square root of 2 pi times 1 over minus I omega. This cosine and that cosine are going to cancel with each other, and then what we're going to be left with is going to be minus 2I sine of omega a. So this is minus 2I times sine of omega a. The minus i's and the i's there cancel. And so this, I'll write it, I'll be in the way, but I'll get out of the way. So the I, and the minus signs cancel. And so what we have is going to be 2 over the square root of 2 pi times sine of omega a over omega. And I'm going to do something a little bit weird here. This is exactly correct, but if I multiply this by a here, and I multiply that by a there, why did I do that? Well, this function right here is called the sinc function, S-I-N-C function. And we'll be using that throughout this semester. Well, I don't know about throughout this semester. We're going to use it to help us prove the Fourier inversion formula. Anyway, so that's what this is going to be. So what we've shown then, let me just put it back to how it is to make it a little more clear like that. And then, of course, 2 over the square root of 2 here. If we wanted to, we could write this as something like the square root of 2 over pi, because 2 over the square root of 2 is the square root of 2, times sine of a omega over omega. Of course, there's different algebra things we can do to write this. Okay, now what we have here is the Fourier transform of this function. So if our function is equal to 1 when the absolute value of x is less than a, and 0 when it's greater than or equal to a, this is our function on the x side. This is the Fourier transform of the function. It's given by this expression right here. We put in a function of x, and we get out a function of omega. This is going to be something that is going to be helpful for us as we solve PDEs and show how to do something called the inverse Fourier transform later on.